Anyway, today we should start our lecture today. So let's talk about how to draw free-body diagram. Now, I suppose you learn pretty much of this in your high school study, but I want you to have a deeper look at the process using the concept of external force and internal force. And I want you to have a clear definitions of a system that you are going to draw the free-body diagram. So I would look at it in more details. So let's return to the case of two person having a tug of the war game. Okay, so they are pulling each other. They are connected by a string, and we have discussed about the force acting on these two person, the tension force Fa and Fb, and also the frictional force Ga and Gb. Now, when we draw a free-body diagram, we actually choose a body. Okay, you can choose the two person as a whole, or you can choose to draw the free-body diagram for person A only, and or you can choose to draw the free-body diagram of person B only. Okay, so whenever you choose to draw the free-body diagram of any of this person or two person as a whole, you enclose it like this with a dotted dashed line, so you can easily see what are the forces acting on this person. Now, for the free-body diagram of person A, you can see there's a tension force Fa, and there's a frictional force Ga. These are the external force. If I define the system now to be person A only, if I define the system to be person B only, then I will see Fb and Ga, Fb and Gb as the external force. Okay. But if I define a system, of the person A and person B as a whole, if I consider them as a system as a whole, then the tension force between them will be the internal force, and I should not count that. Okay, and so I will only count the external force, and the external force is only the frictional force, the friction due to the ground on the body. So the external force are Ga and Gb. Okay, so how you regard what forces are regarded as external force acting on the free-body diagram? It depends on how you choose the free-body diagram. You choose the system. Okay, if you have different choice of the system, you include only one person, include two person, or you include both person, you have different come up with different external force. Okay. Now I would let you see why the existence of external force, how you choose the free-body diagram, how you choose the system for drawing the free-body diagram will affect the external force. Will affect the forces that are regarded external. And I would let you see that Newton's third law is actually important for to guarantee that the Newton's second law set up for different free-body diagram are consistent with each other. Okay, now suppose we have a two block, they are connected by a string, and so the tension force between the two acting on the two block due to the string is Ta and Tb, and there's external force acting on block A is pulled. The block A is being pulled to the right in this figure. Now, suppose I draw a free-body diagram of each of the block. Okay, I draw a free-body diagram of block B, and of course, there's only one external force acting on it, and that's Tb. So by Newton's second law, I have Tb equal to mba. Okay, where A is the common acceleration of the two blocks. But if I draw a free-body diagram of block A, I find two external force. Then the first what's obvious is the external force pulling the block to the right. And the tension force is now also external force because I'm isolating block B from the rest of the system. Okay, so now I have the the total net force acting on block A as F minus TA, because the two forces are in opposite direction, right? So there's a minus sign in TA. And the net force is equal to the mass A multiplied by the acceleration. Now, I now have two equations. If I add up the two equations, I find that the TB actually cancel with minus TA, because TB and TA are pair of action and reaction. They are the interaction force of the two bodies due to the strain. So they form an action and reaction pair. And that's why when I add up the two equations, TA and TB are exactly with the same magnitude, and they will cancel in adding up the equation. So I will end up with the external force F equal to MA plus MB multiplied by the acceleration A. Okay. Now, but if I regard the system as a whole, if I draw a free-body diagram for the system as a whole, including both block A and block B, I will find that the external force F is equal to the total mass MA plus MB multiplied by A. Okay, but that is exactly the equation that I got when I add up the two equations in the first cases. So you see, TB and TA are equal because of Newton's third law. If Newton's third law does not hold, then I will have a difficulty, because if there is no if Newton's third law does not hold, if TA is equal to TB, then I draw a free-body diagram for each of the block and I add up the two equations. It would not be consistent with the equation that I got if I regard the two block as a whole, as a system. So Newton's second law, when applying to different free-body diagram, it will be consistent only if Newton's third law is going to hold. If Newton's third law is not going to hold, then the Newton's second law equation written for different free-body diagram will not be self-consistent with each other. So there's some internal consistency between Newton's second law and Newton's third law. That is a deeper look of the connection between the two laws. Okay, so you can see I cannot write down the correct equation with Newton's second law for different free-body diagram without the presence of Newton's third law. So that is the important idea. Now we are ready to handle more difficult problems because we're clear about those concepts of writing the correct equation for different free-body diagram. So we now handle this problem. Suppose we have a trolley of mass capital M, and a horizontal force applied on the trolley. Okay, a horizontal force F applied on the trolley. And on the trolley, there is a smooth pulley fixed, smooth and light pulley fixed on the trolley. And on the one side of the pulley, there's a hanging mass M2. The mass M2 is hanged before in front of the trolley. And there's a string that passes through the pulley and connected with a mass M1, which is a rest on the top of the trolley, which is a horizontal surface, of course. Okay. Now I consider a system to be frictionless. Okay, so there's no friction between M1 and the surface of and horizontal surface of the trolley. Okay, and I would like to know what magnitude should this force be? Should this external force be in order for the mass M1 and M2 to be staying at rest relative to the trolley? So I want to find what F is such that M2 will not fall down and M1 will not be pulled forward relative to the trolley. So there's only one force that allows me to satisfy this condition. So I'm going to find out that force. Okay, do you understand the question? Now, so we draw free-body diagram for the block M1. The tension force is the only force pulling on it because there is no friction between M1 and the trolley. Okay, so there's the tension force is the only force, and I call this tension force T1 equal to T. So the Newton's second law that I write down is T equal to m1a, where a is the common acceleration of all three objects. Okay, because they are not moving relative to each other, so they have common acceleration forward, and that common acceleration is due to this external force F. Okay. Now I concentrate on the block M2. Okay, for the vertical direction, I know there's a tangent force that is from a string, and since the string is light, it's massless, and also the pulley is smooth, the tangent force T2 that pull the box upwards is the same as the tangent force T1. They are both equal to T in magnitude. Okay, so I just replace my T2 with T. And of course, the block is pulled downwards by its own weight. So the downward force is M2G. But there's an interaction force between the trolley and the block, right? There's a horizontal force that push the block to M forward, right? And that is from the trolley. So I call this horizontal force R. The R is an interaction force between the trolley and the block M2. Now, so if the block is at rest relative to the trolley, that means there's no vertical motion. The block will not fall down, or it will not be pulled up by the string, right? So that means M2G is equal to the tangent T. The weights and the tangent, they exactly cancel each other. Okay, so M2G is minus T is equal to 0, meaning that the tangent exactly balances the weights. But the horizontal direction, the block has an acceleration. It has a common acceleration as the other objects. So for horizontal direction, we write in the second law R, the horizontal force, equal to M2A. Okay. Now you should note that the tangent on the string are equal because we assume no friction on the pulley, and also the string is massless. Okay. Now, if we regard the free object as a whole, as a system, and then the internal force can be neglected. The internal force, we do not count the internal force because we now are regarding the free body as a whole, as a system. So we count only the external force. The external force is the force pushing the trolley, that is F. Okay. And the Newton's second law written for this free body diagram will be F equal to the total mass of the system, which is big M plus small m1 plus small m2. That is the total mass of the system, multiplied by the common acceleration A. Okay. So this is the equation for the system as a whole. Now for the equation of m1 and m2, for m1, I have this equation, tangent equal to m1a. For the vertical balancing of m2, I have m2g equal to t, right? So from these two equations, I can easily solve for the acceleration. The acceleration is m2 over m1g. So I can put this acceleration back to this equation, and I find the horizontal force needed to such that the free object will move together without any relative motion. And that is given by this value. Okay. Now for this case, it may be easier to consider, in this case, it may be easier to consider the system as a whole instead of the free body diagram M. Like you might be tempted to write, to isolate this free body M1, M2. We did it for M1 and M2, but not the trolley M, right? You might be tempted to isolate this free bodies and draw the free body diagram for each of the body. Okay, even for the trolley, but that may not be a good idea because the interaction between the trolley and the two blocks are actually very complicated, and that may confuse you. So it may be better if you can write an equation regarding the free object as a whole, and you apply Newton's law to the system as a whole. And that will allow you to simplify the equation a lot. Okay, so that is a trick. You don't need to draw the free-body diagram for the trolley, but you apply Newton's second law to the system as a whole. Okay. Now, but we want to clarify the concept where we just don't want to avoid the difficult things just because it's difficult. We must be sure that we will be able to do it if we want. So let's take a look at the free-body diagram of the trolley itself. But this is a bit complicated. Okay. Now we should be careful. The trolley is actually connected to the pulley, and the tension force from the string is actually pulls on the trolley because it's act on the pulley, and the pulley is connected to the trolley. So the tension force eventually will act on the trolley. Of course, there's a horizontal force pushing at the trolley, but there's a reaction force also from M2. The trolley is pushing the M2 forward. So the M2, the hanging mass, also has a reaction force that is opposing the forward motion of the trolley. And we have to include that also. So these are the forces acting on the trolley. So you have 4 forces acting on the trolley, right? And you can see these 2 forces are both the tension force from the string, but they act on different direction. This force acts in the horizontal direction, but in the backward direction. And this force is vertical direction, but vertically downwards. Because the 2 forces are the tension pulling the pulley, tends to pulling the pulley backwards and downwards. Okay. So you have these 2 additional forces. You must be careful, otherwise you miss this 2 forces. Okay. Now, if we take into account all the forces acting on the trolley and we draw the free-body diagram, that would be so. And if I apply Newton's second law to the horizontal direction, I have F, the external force, minus R minus T equal to MA, right? These 3 forces are the horizontal force, right? So the vector sum is the net force, okay? But I know from my previous study that that R, this reaction force, is equal to the force that push the M2 forward, and that is equal to M2A, right? And I also know that the tangent force here is given by what? M1A, right? So I have the T equal to M1A and R equal to M2A. So I just put them back here, and I then, of course, I move it to the right-hand side, and I collect a factor of A, and I find that A is in fact given. This is what? This is just the Newton's second law for the system as a whole. So eventually, when I put in A, I get the final answer as before. Okay. Now, of course, there in this case, there is no advantage for you to consider the free-body diagram of the trolley M. Okay, but it's important for you to be clear about those concepts. Okay, what forces are pushing and pulling the trolley, and you should be able to set up the free-body diagram for the trolley if that is needed. Okay. Now I have a challenging problem for you. Suppose now we are playing not with a trolley, with a horizontal top surface. We are now playing with a wedge. A wedge is a triangular shaped block with a horizontal base and an inclined surface on the top. And an inclined surface makes an angle of theta with the horizontal. Now I place a block. The wedge has a mass M, capital M. And now I place a small block of mass ball M on the top of the wedge, on the inclined surface of the wedge. And of course, if I don't move the block, if I don't move the wedge, the block will slide down. But now I push I push the wedge with a horizontal force F, such that the block stayed relatively at rest on the wedge. It does not slide down. Okay, and I would like to find that horizontal force required to do so. Okay, can you grasp the idea? Now, I now draw the free body diagram for you. For the wedge, there's a horizontal force F, and there's a normal reaction because I assume the surface to be frictionless. So the only interaction force between the block and the wedge is the normal force, is the normal reaction. And so there's a normal force pressing down on the surface of the wedge, but that is normal to the surface. Okay, so it makes an angle theta with the vertical. And for the block, of course, it has its own weight mg, and there's a normal force from the surface. And of course, that also makes an angle theta with the vertical. So they are the only force acting on the block and the wedge. Now I neglect the normal force from the ground on the wedge because I know that that must balance the gravity force on the wedge. So I do not consider that, okay, because that must be balanced. So I make it simpler and I neglect the vertical force acting on the wedge. So I now want to set up the Newton's second law equations. Now for the block, I know that there's R in this direction, but I can resolve the force R, the normal force R, in the horizontal direction and the vertical direction. R sine theta is, this angle is theta, so R sine theta is in the horizontal direction. So that is a horizontal equation. And R cosine theta is a vertical direction. Now the condition is that the block is now moving with the wedge together. It does not slide down. So the block does not have any vertical motion. It does not slide down because it's moving horizontally together with the wedge. So it only has a horizontal acceleration, but not a vertical acceleration. So in setting Newton's second law for the vertical and horizontal direction, you know how. For the horizontal direction, you have the acceleration, but for the vertical direction, you don't have the acceleration and all the force should be balanced. Okay, so you should be able to set up two equations for the force acting on the block in the horizontal and the vertical direction. And you can also set up another equation considering the block and the wedge as a whole using Newton's second law. And from this equation, you can solve for the force required to keep the block at rest on the surface. Okay, and you should check whether the answer is reasonable. Now I give you 3 or 4 minutes to do it. Okay, can you try to do it now? At least you should be able to write down these two equations, right? It's not difficult. Any of you who have yes, that's correct. You did it right. Yeah. Any of you who have found the answer? Have you checked that if this answer is reasonable for some limiting case? No. It is not mg tangent theta. It is tangent theta, but not mg, just mg tangent theta. Yeah, m plus mg tangent theta is correct. Yeah, that is correct. Now, let's do it together, okay? I will illustrate to you some of the important ideas by using the pad. I draw it not very well, but I hope you will be able to understand it. Now, the important thing is the three-body diagram here. With the block. Now, the horizontal component is R cosine theta. Sorry, R sine theta, sorry. So this is the horizontal component. So this is sine. And since the block is in horizontal acceleration, right? So it's equal to ma. And vertically, in the vertical direction, the block is at rest because it's not sliding down. So R cosine theta, the vertical force, is balanced by the force of gravity. It's equal to mg. So you can easily solve. You can easily solve for the acceleration. You divide the two equations and you get rid of R. And so A over G is just what? It's just sine theta over cosine theta. And that is tangent theta. Is that right? When you apply, when you take the two body as a whole in a three-body diagram and set up Newton's second law, the internal force are not important. The internal force will not be considered if you take the two body as a whole. And in that case, you will have the total mass of the system as m plus m, right? That is the total mass for the system. You now regard this as a whole body. So this is only the external force. The horizontal force is only the only external force. And so the external force is equal to the total mass of the system, m plus big M plus small m, multiplied by the common acceleration A. Now this is possible because the two bodies are moving as a whole. They are not sliding relative to each other. Okay. If the two body is not moving with the same acceleration, then you have to be very careful. You have to require separate treatment. We will know how to deal with that. But in the chapter of momentum, we will know how to deal with that. But now, let's, in this case, we only have common acceleration. So we don't need to separate the two bodies. We can consider them as a whole. And so we can write down this equation for the two bodies as a whole. Okay. If the two bodies are sliding relative to each other, then you must be careful. You have to use the center of mass concept in applying Newton's second law to the system as a whole. But that will be taught only in the chapter of momentum, not here. Okay. Now, so with these two equations, the answer is clear. You now have A equal to G tangent theta. So you have M plus M G tangent theta as the answer. Is that right? Now, let's check whether this answer is reasonable. Do you think this answer is reasonable? Let's check for the special case. The special case are when theta tends to 0. The wedge is actually horizontal, right? So that is the condition for horizontal surface, right? Now for the horizontal, if the surface of the wedge is horizontal, then you don't need the force. You don't need any force to maintain it in equilibrium. It will stay at rest on the top surface because the surface is horizontal, right? So that means when theta tends to 0, this is a horizontal surface, and the force F tends to 0 also. That is apparent because when theta tan is 0, tangent theta is 0. So F is of course 0. So that agree with our intuition, right? How about if theta tends to 90 degrees or pi over 2? We find that the surface is now becoming vertical. Now for this case, we draw it like this. It's almost horizontal, okay? The surface is almost horizontal. And now for this case, we have this angle theta very large, almost equal to 90 degrees. So the surface is almost vertical. This surface is almost vertical now. Not for vertical surface, and you don't have friction, anything resting on this surface will obviously fall down, right? Because you don't have a friction to oppose that. The surface is vertical and you don't have friction. So everything resting on this surface must slide down under gravity. So there's no way for you to prevent it from sliding down. So that means you need an extremely large force. If you are getting very close to 90 degrees, you need an extremely large force to keep the body in equilibrium. And that is exactly observed. When the angle is 90 degrees, you see from this tangent, when the angle is 90 degrees, tangent theta tends to infinity. And so the force will tend to infinity, right? That is expected. Because if it's almost vertical, then you need a very large force to keep the object in equilibrium, okay? So after you write down the answer, you check it, whether it is physically agree with your intuition, okay? So I leave it to you. I shared it with you in the chat box, okay? Let's go back. Now let's discuss a little bit about vertical circular motion. In your high school study, you learn about horizontal motion, horizontal circular motion, okay? That may happen on the surface of a smooth table, or you swing it, the object around, so it moves in horizontal circle. And in those cases, the only net force acting on the object, we don't consider the vertical motion. The only net force acting on the object is a horizontal force. The vertical force are balanced. And the net force is equal to the centripetal force, right? It comes from maybe the tension in the string that provides centripetal force for the horizontal circular motion. But now we make the circular path vertical. Suppose you now is holding one end of the string, and the other end of the string is connected to a small bit, and you swing it in a vertical circle. Instead of horizontal one, you now swing in a vertical circle. Now, so we want to know when the object is in different position, what forces will be providing the centripetal force? Okay, we want to know that. Now, this question is not that trivial because we now have two forces acting on the block, on a bit instead of one force. The first one is, of course, the force due to gravity. It's always vertically downwards. But now the tension from the string, it comes from all angle. When the bit is at the bottom, the tension is vertically upwards. When the bit is at the top of the circle, the string is pulling it down, right? So it pulls it vertically downwards, okay? And so the direction is different from the direction is different in these two cases. And the most complicated thing is that if the string now makes an angle theta with the vertical, the tension is towards the center of the circle, also making an angle theta with the vertical, but the gravity is always downwards. Okay, so you have to resolve the component to find the centripetal force. Okay, so we handle each of these case separately. Now at the bottom, when the bit is now at the bottom, the tension and the weights are in opposite direction, right? The tension is pulling up, the weight is down. But since the body is now in vertical circular motion, it must have a centripetal force. And the centripetal force is given by the net force, which is T minus mg. The centripetal force is given by mv squared over r, where v is the velocity, the speed of the object at this instant. We simply apply the net force being equal to the centripetal force. But since the tension and the weight are in the opposite direction, there's a minus sign before the weights. And the tension force should be larger than the weights in order to provide the centripetal force upward. Okay. Now at the top, when the bit is at the top, both the tension and the weights, they are pointing downwards. And so we add up the two force T plus mg to find the total net force. And the total net force is equal to the centripetal force. Okay. Now how about at a general angle? The things are tricky because we now have to resolve the force along the string, because it is this direction that points towards the center that provides the centripetal force. So in order to find the centripetal force, you have to find the component of all the force along this direction. T is already in this direction, so we don't have to resolve it. But the downward force of gravity mg has a component along the string. The component is mg cosine theta. Okay, this angle is theta, which is the same as this angle. So we have T minus mg cosine theta be equal to the net force, and that is mv squared for r. Now that is a centripetal acceleration that provides the necessary force, the centripetal force for the circular motion. But you should be careful. The V is now also changing in magnitude, not only in direction. Why? Because there's another component, mg sine theta. You see this component of the weight, mg sine theta, is in the tangential direction. And that actually will decelerate the velocity. It will change the magnitude of the velocity. So that is not a constant speed circular motion. The speed of the circular motion may be changing with time. So the V of the bit at the bottom may not be equal to the V, the magnitude of the velocity, the speed of the bit at the top. It will not be equal to the speed at a general angle. The speed keep on changing with time, not just the velocity direction, but speed itself may be changing. So how will the speed change? Oh, that depends on the condition given in the problem. If the bit is now rolling down a certain track, certain circular track, vertical circular track, then you may have to use the conservation of energy to calculate the velocity, to calculate the speed at different position. If this person is swinging the bit a little bit, there's a external force pulling it, accelerating it, then that would be, the problem would be quite difficult. Okay, so it depends on situation. Now I would like to share with you this. Now suppose, now have you seen this roller coaster? Have you ride this roller coaster in Ocean Park or Disneyland? When you are at the top of a vertical loop, okay, you do not feel your body being detached from the roller coaster. You feel as usual. You feel your body is attached. You're still attached to the roller coaster. You are not falling down, right? You are not dropped down by the roller coaster, right? But why? Now the trick is due to the normal force. There is a normal force acting on your body by the seat. The normal force is still there. And the normal force keeps you attached to the seat without letting you falling down. And the normal force is sufficiently large to keep you on the seat when the roller coaster is passing through the loop at the top of the loop at a sufficiently high velocity. Now let us see why. Now because at the top of the loop, the normal force and the weight, your weights, are in the same direction. They are both vertically downward. So they add up together, N plus mg, they add together. N is the normal force, mg is all weight. The two forces add up together to provide the centripetal force mv squared for r. Now let us move this equation a little bit. Let us move the term mg to the right. So the normal force will become mv squared for r minus mg. And you can see that the normal force will always be greater than 0 if mv squared for r is larger than mg. That is, when you pass the loop, the top of the loop, when you are sliding down from a very great height and you pass the top of the loop at a sufficiently large velocity such that mv squared for r is larger than mg, the normal force is larger than 0, which means that your body will be attached to the seat because the seat is now pressing on you with the normal force. So you will be attached to the seat without being detached and fall down. Okay, so that's the condition for you to be attached to the seat without falling down. Okay, and it hinges on sufficient velocity. If v is not large enough, then the n may be 0. You hinge on the fact that the v is large enough such that v squared for r is larger than g. Otherwise, it will fall down. Okay. Now the similar thing happened to this demonstration. You swing a bucket of water in a vertical circle, and at the top of the loop, of the circular loop, the water does not fall down because, like this equation, there's a normal force pressing on the water due to the bucket. The normal force is not 0 because I have a sufficiently large velocity when I pass through the top of the loop. So when v is large enough, n is always there, and the role of n is not make the water falls down, but it's making the water to turn around in a circular motion. It provides a centripetal acceleration. It's just changed the direction of the velocity. It is not letting the water falling down. Okay, so that is a trick here. Now this is an interesting demonstration called a centripetal track. I will show it later after having a break. But before having a break, I want to show you a video that I took with Kalina in a show. And that involved a toy that I just showed you, this toy. Now this cup is attached to a plastic holder, and there's a handle here, so you can swing it in a vertical circle. If you put some water inside cup and you swing it fast, the water will not fall down, even if it's at the top of the circle. Okay, so I actually have a video with Kalina, 吉林公主, in RHK, and that will show you. I'll show you this. Now I apologize that the video is in Cantonese, but you still can get the essential idea. Okay, just by looking at the video, and I will explain a little bit.
咁多種力啦，我有一種力咧，我成日都會遇到嘅，就係離心力，因為一俾人嚇一嚇我個心就嚟一嚟㗎啦，係咪咁樣解釋嘅咧？
誒，嗰個係你心血少所以驚啫。我諗你係搭緊過山車嘅時候有嗰種感覺係咪咧？
係啊。
咁但係其實離心力即係過山車嗰個原理咧，其實都可以講得到嘅。嗱，我呢度有個小玩具。嗱，你見到啦，呢度有個兜喎，咁有杯水啦，個兜就冇黐住杯水嘅。你玩過過山車未啊？過山車會打圈噶嘛？
係啊。
我而家就玩過山車俾你睇啦，用個杯嚟玩。好，嚟啦！
哇！咦，啲水係好似黐實咗個杯，而個杯又好似黐實咗呢一個柄咁嘅喎。
係啊，冇跌落嚟㗎。嗱，其實咧，我頭先咧就將個杯向前揈啦。如果我乜嘢都冇托住佢嘅話咧，個杯水就會飛走咗啦，係咪？咁但係咧，其實咧我有個力嘅，就係由呢個手柄啦，我拉翻佢轉頭。咁佢又想向前走喎，但係我而家拉翻佢轉頭喎，咁最後會發生咩事咧？就係佢繞住我咧，做一個圓周運動咯喎。咁當個杯係壓住，有個力壓住喺啲水嗰度，令到佢改變方向嘅時候咧，其實啲水咧就反而咧就唔會離開個杯，咁所以咧調轉咗都唔會跌落嚟啦。
所以玩呢個過山車就好似嗰啲水咁樣，就壓住咗喺個過山車嗰度。
喺個過山車裏邊嘅感覺咧，好似俾人向外拋嘅，但係其實咧個過山車係壓住你㗎，令到你唔會跌落去㗎。
咦？我想同杯水玩過山車，你信唔信我啊，博士？
你啊，我行開啲先啦。
好，我相信物理。
好，
嚟啦！無敵風火輪。
掂啦，係咪？
得咗啊，博士！咦，咁博士，我又想問啦，頭先呢個過程當中咧，同我哋之前提嘅作用力同反作用力咧，係咪都顯示到出嚟嘅咧？
嗱，其實咧有個方法顯示到嘅，除咗呢個杯之外咧，我哋仲需要個磅。個水杯咧就唔夠重，今次咧我整啲重啲嘢俾你玩，一袋書嚟嘅，
好重啊！
咁一陣間咧照揈就得㗎啦。不過咧你係企喺個磅上面揈，睇你揈嘅時候，你身體嘅重量咧有冇變化
？OK， 好啊，嚟咯
嚟咯
！OK， 1、2、3，
係見到啦，輕咗幾 kg，又重翻幾 kg，哇，得意！
輕咗幾 kg 咁多嘅，點解嘅？
咁個原因咧就係咁樣嘅。當你個袋咧去到你嘅手下邊嘅時候咧，你有個力拉住個袋噶嘛，咁嗰個叫向心力啊嘛。所以我拉住個袋嘅時候咧，牛頓第三定律就話俾我聽，有個反作用力啦。個袋就拉翻我嘅手轉頭，咁就將我身體壓向下咯。咁於是我體重咪增加咗咯。
咁我知啦，即係咧到我揈個袋向天嘅時候咧，其實佢又拉咗我上去，
所以你嘅體重咧就會減少咗啦。所以你就時輕時重啦。
咁我永遠將個袋一路揈嘅時候，我咪可以達到我人生最輕嘅體重咯。
哦，睇你揈得有幾快嘅啫喎！
博士，你幫我睇下我最輕嘅時候係幾輕啊！快啲睇下。
女仔都係貪靚，都係冇辦法。
So, do you know what's happening in the video? Is she swing the bag in a vertical circular motion? Now, so let's draw a 3-point diagram to see what actually happens. Now, if I draw a 3-point diagram of a body, this is Kalina, and of course, she's acted by her own weights, which is in the vertical downward direction. I prefer to label his mass by big M because I need the small m for the back. Now, when the back is in the vertical direction, is in the lowest position, the weight is downward, right? But there's a tension force from the string pulling me up. So that produces a reaction force on her body. And so her body will be experience a downward pulling force. These two forces are action and reaction. Okay. Now, so in this case, there are two forces pulling Kalina downwards, and that is given by T plus mg. So this is her apparent rate. Her apparent weight will be increased due to the downward pulling force from the body. Now, how about when the bag is in the top position? Now the weight is still downwards, okay, and the pulling force from the string is of course also downwards, right? And you can see that it will produce a reaction force on Gitling, and that reaction force is upwards, is pulling her upwards. So her weight is downwards. So these two forces are in opposite direction, and so her apparent weight will then be mg minus t instead of mg plus t. So you can see her apparent weight will be lighter, will be less when the bag is at the top, and her apparent weight will be larger than mg, will be larger when the bag is at the bottom of the circular track. So that explains what is observed on the beam balance, because the beam balance actually measures the apparent weight mg plus t and mg minus t. Okay. So I let you have a break for 10 minutes. Okay. I share with it. Now, but be careful. The velocity of the bag at the bottom may not be the same as the velocity at the top. And also, the tension force here in these two cases, they are not equal. And so there's not so straightforward to calculate the change in apparent weight by using T. It depends depends actually on the speed, the difference in the speed between the two cases. Okay. So let's take a break for 10 minutes, and we will come back to discuss more about the vertical circular motion, and also we will discuss about frictional force.